I'm Maura O'Sullivan, and I'll be discussing the topological properties of yarn and textiles. Before we get into those properties, it's important to understand how a single strand of yarn turns into a textured fabric with varied dimensions. As you can see here, when knitting, one creates a series of slip knots interwoven with each other. This changes the yarn in several ways, both physical and mathematical, and creates a two-dimensional lattice surface known to physicists as a metamaterial. Metamaterials are materials which derive their properties from small internal structures rather than the chemical composition of their parts. Now, on a basic physical level, knit stitches can be interpreted by way of knot theory, which is the mathematical study of circles with embedded crossings which can't be tangled, or, as we know them, knots. When those knots create a knitted metamaterial, the microstructures, in this case slip knots, gain physical properties beyond those of the yarn itself. This is the stress-strain curve. Also known as Young's modulus, it describes tensile elasticity, which, in a simplification of its equation, is defined as tensile stress over tensile strain. In other words, Young's modulus describes how much stretching an object or material can withstand. As you can see, this initial point on our generic graph of Young's modulus represents the point at which a material is permanently deformed and can no longer return to its original shape. Further along the x-axis, as strain increases, materials reach the fracture point and break entirely. Now, yarn has a low modulus. It snaps easily compared to most other materials. However, when knit together, yarn gains the ability to stretch far beyond its normal fracture point. Knit fabrics have much higher moduli and can withstand far more abuse before breaking or deforming than yarn can when it stands alone. Cooler yet, those changes to Young's modulus between yarn and fabric vary depending on the order of stitches. Knitting, a stitch which uses a regular slipknot, and purling, a stitch which uses an inverted slipknot, can be structured into thousands of different fabrics with different tensile elasticities and topological properties. On top of that, some scientists suspect that there are infinite possible stitches beyond those two basics, which implies infinite potential for the physical properties of knit textiles. On the mathematical side of things, we're going to talk about the topology of a knit surface. Topology is the geometric study of objects which are preserved under continuous deformations. If you've ever made a human knot during a team-building activity, that's topology. You can shift positions, crumple objects, stretch them, even turn them inside out, but they must maintain their integrity without separating pieces or attaching anything new to the system. Fabrics that have been knit flat form a type of topological surface called a manifold. These are shapes and objects which have Euclidean spaces locally but not globally. More simply, on a small scale, manifolds have repeating structures observable on a two-dimensional coordinate plane. This phenomenon can be visualized with a knit blanket. Looking closely at the stitches, the repetition is graphable. However, as we see when I do this, a blanket is not a perfectly two-dimensional surface. Since the blanket overall is not mathematically flat, the repetition only exists on the level of single stitches, which is what makes the blanket a manifold. This manifold structure makes knitting ideal for certain types of modeling, as fabric is far easier to manipulate than computer models. Knit fabrics are becoming popular for mathematical modeling among a cult following of physicists and material scientists, as a matter of fact, some of whom are also researching how fabrics drape and varying types of stitches impact its behavior. Now, it's important to note that not all knit surfaces are manifolds. For instance, a garment with pockets doesn't have Euclidean spaces at the seams because multiple pieces of flat knitting are stitched together, which changes the structural composition of the fabric. Still, physicists have made all sorts of topologically fascinating shapes. My personal favorite is this Klein bottle, which was made by mathematician Sarah Marie Belcastro, and, true to models of Klein bottles, only has one surface across the entire area of the construction. Finally, let's talk about the applications of this information. The mathematical properties of handmade textiles have gone relatively neglected in academia until recently, but researchers like Georgia Tech's Elisabetta Matsumoto are harnessing this 2,000-year-old technology to better understand the topological properties of knots, as well as the mechanical properties of human tissues. It's crazy that something with as many flat surfaces on its face as a hat can be made from a single length of string, but that crazy just might teach us about the geometry of materials and ourselves.